If chemicals once formed never changed, the world would be a very boring place. Our universe is enriched by the great principle that elements and compounds combine in chemical reactions to form new materials. In this lecture, I'm going to introduce two major aspects of chemical change. The first topic is phase transformations. This is the property of some materials to alter their atomic structure when they're subjected to heat or subjected to pressure or some other external influence. And as we're going to see in this and in future lectures, phase transformations play key roles in the dynamics of Earth and in life. Then I'm going to introduce some of the many kinds of chemical reactions by which one group of elements or compounds transforms to chemical substances with totally new properties. This lecture then is the real meat of chemistry. Change is a hallmark of the material world. Wood burns, water boils, glue hardens, eggs cook, dead organisms decay. These obvious physical transformations reflect the change in arrangement of atoms and their chemical bonds. In the last lecture, we examined changes of state between solids and liquids and gases. We had the phenomenon of melting and freezing, boiling, and the like. By the way, all of these changes are the result of thermal vibrations of atoms. At lower temperatures, atoms and molecules don't vibrate as much. See, the atomic scale structure is so critical to properties. But as you go to higher temperature, atoms and molecules vibrate more and more until they become so agitated they become a liquid. And then those liquid molecules and atoms fly off and become a gas at even higher temperatures. And at the highest temperatures of all, a plasma forms because the gas molecules hit each other and strip off electrons. In this lecture, we're going to examine two other common ways of rearranging atoms. They're called phase transformations and chemical reactions. Now, many common substances occur in more than one arrangement of atoms. We saw, for example, that there are 18 different isomers of octane. Remember, that's the carbon-based molecule that has 8 carbon atoms and then hydrogens all around. So it's C8H18. So there are 18 different molecular structures for that compound alone. Now, the change of a substance from one atomic arrangement to another using the exact same collection of atoms, particularly from one solid form to another solid form, is called a phase transformation. One of the most dramatic examples of phase transformations is provided by the element carbon, element 6, which occurs naturally in two forms. It occurs in the common black form called graphite and in the extremely hard form called diamond. And these two compounds differ remarkably in their physical properties and their behavior. Soft black graphite is one of the softest materials known. It's used as a lubricant. It's the lead in your pencil, and as you write across a page, you strip off layers of graphite structure. It's so soft. But diamond is colorless. It's hard. Indeed, the hardest substance known, and yet it's composed of the exact same element, carbon. We now know that these differences are the result of the difference in crystal structure of these two forms. Graphite, soft graphite, primarily has van der Waals bonds holding layers together, and you can see those flat layers of carbon atoms in which each carbon is linked to 3 others in a planar arrangement. That's the low-pressure, soft form. And it's the van der Waals bonds that make it soft. Diamond, on the other hand, has a rigid, 3-dimensional network in which every carbon is connected to 4 other carbons. This is an incredibly hard, incredibly strong structure because of this cross-linking, the 3-dimensional arrangement of bonds. And so diamond is the hardest known material. More than 200 years ago, scientists began to explore ways in which they might transform common graphite into diamond. And most of the early attempts, as you might expect, focused on extremely high temperatures. One of the pioneers in this work was Henri Moissan. He's the French chemist, the brave chemist who first isolated fluorine. Moissan used a carbon arc furnace, but to no avail. What he did was he had 2 graphite arcs, 2 electrodes, and he passed a huge current through that, causing flames and gouting fire at thousands of degrees. He hoped that diamonds would form in that flame, in that arc, but he found nothing. Indeed, it was not until the 1870s that geologists discovered the key to making diamond. Until the 1870s, diamonds were only known from gravels, from stream deposits, some of them in India, some of them in Brazil, some in South America. And these diamond deposits were just loose stones in the ground. But amazing discovery occurred in South Africa in 1866. 2 children were playing in a South African stream bed, and they found a shiny pebble that weighed 20 carats. It came to be known as the Eureka diamond, and that Eureka was the beginning of the South African diamond rush. 2 years later, an 83.5 carat stone called the Star of South Africa was found, and that triggered the major influx of miners scouring the South African countryside looking for the precious stones. Eventually, what they found revolutionized the diamond trade. They found the first examples of diamonds in their native rock, a rock called kimberlite. And it turns out that that rock told an amazing story. Kimberlites are volcanic rocks, and they're erupted from deep within the earth. In the final stages of these eruptions, the rocks come whooshing to the surface at the speed of sound, blasting out of the surface, showering diamonds over hundreds of square kilometers. In a few places, the plugs, the necks of these volcanic rocks filled with diamonds and diamond-bearing material are still in the ground, and that's where the great South African diamond mines, such as the Kimberley mine, were found. Geologists quickly realized that diamonds come from great depth in the earth, and that pressure is the key to its synthesis. Well, using theories that relate a material's structure to its stability, scientists were able to calculate what those pressures were. Not only does diamond require tens of thousands of atmospheres pressure, it also requires temperatures over 1,000 degrees to make the carbon atoms wiggle enough that they'll break bonds and reform from graphite to the diamond form. For decades, many people tried and many people failed spectacularly in their attempts to synthesize diamond from graphite at high temperature and high pressure. One example was James Ballantyne Hannay, a Scottish chemist who tried an intriguing way of approaching the diamond synthesis problem. He had gun barrels, and he packed them full of carbon-rich materials. He then welded the barrels shut and stuck them in a hot fire. Well, huge temperatures and pressures developed inside the gun barrels, but eventually the barrels exploded. So what Hannay did was went to larger and larger gun barrels, some of them up to several inches in diameter, which progressively exploded at higher and higher pressures with more and more violence. Indeed, his workmen were so afraid of this experiment that they may have actually seeded his experiments with a few diamonds, which satisfied the old man who eventually gave up the pursuit. But Hannay did not make diamonds. Another bizarre attempt was made by Baltzar von Platen, a Swedish inventor, a mad genius he was called. In conjunction with the Swedish General Electric Company, von Platen had an idea for a machine in which he had a large sphere of metal split into pieces, the pieces forcing themselves down on a tiny carbon sample. This is what von Platen said when he described this strange machine. He said, "You must let your machine go to meet death by dividing it up into pieces, but you must give these pieces the shape that the machine itself would have wished, had it been a living organism. And then you will be able to make diamonds." That's a strange kind of rhetoric for a scientist. Well, in any case, von Platen used a split sphere device in which he divided up a sphere into 6 anvils, each of those anvils pressing down on the face of a cube. The cube was made of graphite. Each of these experiments then was jacketed in copper, immersed in a huge water tank, pressurized to thousands of atmospheres, and an inner core of thermite, a high-temperature explosive, was set off in order to generate the pressure and temperature needed to make diamonds. And the Swedish company failed time and time again at the cost of countless hundreds of thousands of dollars. In fact, it wasn't until 1954 that a team of scientists at General Electric in Schenectady, New York, succeeded in making the very first synthetic diamonds. This was an amazing team effort. It showed the can-do attitude of the post-war era, and General Electric said, we're going to make diamonds. And they said, even if we don't make diamonds, something interesting is going to happen, because high temperatures and high pressures, that's an unexplored area of chemistry. And interesting things they did indeed find. The way they went about it was to first assemble a team of scientists. They had materials engineers, they had chemists, they had physicists, people who approached different aspects of this diamond-making problem. They had experts in electrical heating so they could get high temperatures. They had experts in materials, super hard materials, so they could make pistons that would ram their graphite to higher and higher pressures. Well, it took several years, fits and starts, but eventually in December of 1954, the first synthetic diamonds were manufactured by General Electric. And in fact, in a matter of a few months, they were producing buckets of diamonds in a commercial process. Today, diamond synthesis is a worldwide enterprise of vast proportions. Every year, more than 100 tons of synthetic diamonds are manufactured in plants around the world. That's more diamonds manufactured each year than all the gemstone diamonds that have been mined since biblical times combined. These synthetic diamonds are usually in the form of very fine-grained grit. This is a small sample of General Electric man-made diamond. And these are beautiful crystals. Under the microscope, you see tiny facets and other sorts of tiny crystals, perfect crystals. These abrasives are used to transform our society in subtle sorts of ways. You don't recognize synthetic diamonds in your day-to-day life, but they have changed the things that you can do and the way you live. If any of you wear eyeglasses and have gone into an eyeglass store and come out an hour later with a pair of eyeglasses, that's diamond technology, because now diamonds are so cheap that any little store can have a diamond grinding tool. If you've ever walked by a roadway which is quietly being repaired rather than with big jackhammers that make all that noise and tear up the surrounding roadways, but surgically removed with a diamond saw, that's a diamond technology, because cheap synthetic diamonds are now available to everyone. You may have also seen some of the beautiful building stones that now adorn our cities. Granites that have been polished, other very, very hard rocks you never would have seen 25 or 30 years ago facing buildings, but now they're commonplace because you can cut and polish these stones with diamond. And indeed, you can have them on your kitchen counter, on your kitchen floor, a whole variety of new beautiful stones that never before were available for commercial use. Okay, let's shift our focus now from diamonds, which is the abundant element carbon, to another important substance, water. Solid water is remarkable for its many phase transformations. As temperature and pressure are varied, H2O, water, undergoes at least 10 different kinds of transformations to different crystal structures. Each of these different materials, all of them H2O, all of them solid in crystalline form, has a different arrangement of those H2O molecules. So they're different crystal structures with different properties. In a diamond cell, which I showed you last time, you can look through the diamonds and actually watch these crystals transform from one form to another to yet another. The phase diagram of water, which has pressure plotted against temperature, shows that in various pressure temperature regimes you have these different solid forms. This is a very useful device for scientists, because then you can predict at what particular temperature and pressure you want to study water, go to it, and see that crystal form. Well, not all phase transformations result in such drastic changes of crystal structure. I want to tell you about one of my very first research projects as a crystallographer, when I began to study crystal structures at high pressures. I was interested in a beautiful red mineral called gillespite. This very rare mineral of barium copper silicate is found only in a few locations, for example in California, but it forms magnificent square red crystals. The thing that's so neat about this mineral is when you take it up to high pressure to about 20,000 atmospheres, that beautiful red crystal suddenly, instantaneously changes to a deep blue color. Now, we know that all physical properties are the result of the atoms and how they're bonded together. So there had to be a change in atomic structure, and that's what I wanted to study. I studied the crystal structure at low pressure and at high pressure and found a very interesting change. At low pressure, there are iron atoms in this mineral that are surrounded by a perfect plane of 4 oxygens, a square of oxygens with iron in the center. There's an electronic transition, an electron jump in that iron atom that gave the mineral its red color. But as you go to higher pressure, that square plane buckles. And so 2 of the atoms go a little bit higher, and 2 of the atoms go a little bit lower than the iron. You no longer have a plane of atoms, and the electronic structure of the iron atom changes too. That subtle change in the iron causes the color to change from red to blue. It's an absolutely magnificent phase transition, and one that's stayed with me for all those years. Well, the most dramatic phase transitions of many compounds occur at extremely high pressures, where scientists expect that all compounds, every compound, water, gas, diamond, whatever compound you can think of, will transform to a metal. Now, the reason is this. As you go to high pressure, you're squeezing the atoms closer and closer together. Eventually, the electrons start to overlap from adjacent atoms, and that's an unhappy situation for those electrons. They want to get out of there. And so what the electrons do is delocalize, and they become a metal. Recently, scientists have actually turned oxygen into a metal at 1 million atmospheres, and they've done it with sulfur as well. But one of the great holy grails of high-pressure physics is to turn hydrogen, element number 1, into that most primitive of all metals. This is a challenge that may require 5 million atmospheres of pressure, and a lot of people are still trying to do that. One of the great things about high pressure is that it holds the promise for producing so many new materials. As you squeeze virtually any compound, it will change, it will transform again and again and again. So simply by applying pressure to all the known compounds, we could conceivably triple or even quadruple the number of known materials that are available to us. That's the lure of high pressure. Now I want to switch to the second topic of this lecture, chemical reactions. A chemical reaction occurs when 2 or more chemical substances combine to form a different substance, or when one chemical breaks down to form other materials. Given the relatively small number of common chemical elements, certainly no more than about 80 elements that are in our daily lives, it might seem that chemistry is a rather limited field. After all, with only chemical elements, how many combinations could there be? So I want to take a second to look at this question of combinatorics, combining the elements to see how many combinations we might have. First, I want you just to think about a 1-to-1 ratio of 2 elements, the binary compounds. Well, we have 80 elements, each of which can combine in a 1-to-1 ratio with the remaining 79. So that's 80 times 79. And you have to divide by 2 because a combination of A with B is the same as a combination of B with A. That gives you a total of 3,160 1-to-1 element combinations from the common chemical elements. Well, you need to try each of those 1-to-1 combinations, those 3,000 plus combinations, at many different temperatures, at many different pressures, and of course at many different ratios, because you might try 100-to-1 or 1,000-to-1 or 10-to-1 or 2-to-1 or whatever you want to do, all those ratios. So that leads ultimately to millions upon millions of combinations, even with the binary compounds. And then you have to consider 3 elements together, or 4 elements. There are more than 1 billion different combinations of 5 elements in a 1-to-1 to 1-to-1 to 1 ratio. And then you have to vary the ratios. Then you have to vary the temperature and you have to vary the pressure. For all intents and purposes, chemistry is a vast, infinite subject of study. Indeed, you can't just go into the laboratory and randomly mix chemicals and hope to have anything useful come out. You have to have a plan. So the art of chemistry is the ability to predict which chemical combinations are going to provide something useful, which will give you a new synthesis condition that can be used to help humanity. Now, all chemical reactions involve the rearrangement of electrons through the breaking and the reforming of chemical bonds. You have to take atoms apart, stick them back together in a new way. Now, while there are countless specific reactions, and I can't possibly go into all those, most fall under a few general types of reactions. I'm going to discuss 3 of these kinds of reactions. I'll look at oxidation-reduction reactions. I'm going to look at solution precipitation reactions. And finally, polymerization and depolymerization reactions. Now, oxidation-reduction reactions include many of the common reactions with oxygen, which is a highly reactive gas. It's the gas that forms 20% of our atmosphere that we breathe. Oxidation reactions occur when oxygen, or any other element for that matter, accepts electrons. Remember, oxygen is element 8. It wants 2 electrons. And when oxygen gains those 2 electrons, that's an oxidation reaction. Typically, oxygen reacts with a metal. So, for example, if you have iron, a metal, iron gives up electrons, oxygen takes them, and you can form the chemical reaction called rusting. So you form iron oxide from iron metal and oxygen. There are other much more rapid forms of oxidation. For example, burning. Remember when we talked about hydrocarbons a couple of lectures ago, compounds of carbon and hydrogen. If you burn a hydrocarbon, you produce hydrogen oxide, H2O or water, and carbon dioxide, the oxide of carbon. And you get lots of heat and you get lots of energy. So all of these familiar oxidation reactions produce heat as a byproduct, and that's one of the reasons why they're very useful. Now, humans and other animals also use oxidation reactions. In fact, when we breathe in oxygen, we're able to gain energy by oxidizing various hydrocarbons that we eat as our food. There are other elements that undergo this kind of oxidation reaction too. Recall the dangers of fluorine, which is the most violently reactive of all elements. Fluorine, element 9, wants to gain 1 electron, and so it oxidizes almost anything. That's why fluorine gas is so dangerous, and it killed or injured so many early chemists who tried to study it. Okay, the opposite of oxidation is called reduction. It's just the opposite. It's when oxygen gives up electrons. Now, since we're such an oxygen-rich atmosphere, and since every oxygen atom wants electrons, reduction reactions don't often occur just in the normal atmosphere. But in a very, very hot fire, you can produce a reducing environment. And that's how iron ores are smelted. Now, iron ore is an iron oxide. So you take iron oxide, you put it in a hot furnace along with charcoal, that's carbon, and typically calcium oxide, that's called lime. The typical reaction is that the iron oxide combines with carbon to form carbon oxide, CO2, or carbon dioxide, and iron metal. And that's how an iron smelter works. By the way, the reason you add the calcium oxide, that lime, is just to lower the melting temperature of the whole mix so you get a much faster reaction. All of the oxidation-reduction reactions involve the movement of electrons. That's the key here. So when iron metal is oxidized, the iron atoms lose electrons, the oxygen gains electrons. When iron ore is smelted, on the other hand, the iron atoms gain electrons. And this leads to a very useful mnemonic, oil rig. Oxidation is loss, reduction is gain. Oil rig. Batteries, by the way, rely on oxidation-reduction reactions. You take a battery, and you'll see that there's a positive and a negative terminal. The two terminals on most batteries, then, are places where oxidation and reduction reactions occur. The negative terminal of many batteries is in contact with a chemical such as zinc metal. And that zinc metal readily gives up electrons and enters solution as zinc 2+ ions. Now, the positive terminal of the battery is in contact with a solution containing metal ions, typically copper ions, Cu2+ ions. And as the battery is used up, copper is precipitated on that positive terminal. So you have a transfer of electrons with oxidation and reduction reactions going on. Now, when a circuit of the battery is closed, electrons flow from one terminal to the other. When the battery goes dead, it means that either all of your oxidants or all of your reductants have been used up. And quite a few batteries can be recharged just by forcing electrons to flow the other way, and you reset up the oxidants and reductants, and you can use your battery over again. By the way, as I mentioned, life obtains all of its energy in the same way, through oxidation-reduction reactions. Plants reduce CO2 to carbon, hydrocarbons, and other fuels. Animals oxidize plants and get energy back that way. Well, there are many other kinds of reactions that occur in day-to-day life. One of the most important has to do with water. Water and many other liquids have the ability to cause solution and precipitation reactions. For example, salt dissolves in fresh water, and a saturated saltwater solution, by contrast, if you evaporate it, precipitates out salt crystals. So those are examples of precipitation and solution chemical reactions. All of the classic methods of wet chemical analysis for rocks and minerals, all of them developed in the 19th century, involved a careful sequence of solution and precipitation reactions, weighing the solid products that were precipitated out. Another kind of solution chemistry that's very important has to do with acids and bases. An acid is any chemical that produces positively charged hydrogen ions when added to water. Water is H2O. If you split the H from the OH, you have a negative OH, a hydroxyl group, and a positive hydrogen, an H. If there's an excess of positive H's, that's protons, then you have an acid. Hydrochloric acid, HCl, for example, when added to water, yields H plus in the water and Cl minus. And so that excess of H plus is the acid in hydrochloric acid. There are many other acids. Fruit, for example, often is very strong, has a large concentration of mild acids, things like citric acid. Car batteries use a very strong acid called sulfuric acid. In each case, these are chemicals that, when added to water, release hydrogen as isolated ions. Now, bases include all sorts of chemicals that produce the negatively charged OH minus group, the hydroxyl group. So, for example, sodium hydroxide, NaOH, when added to water, produces sodium ions, which are positive, and OH, hydroxyls, which are minus. And so you get a concentration of that base material. And acids such as milk of magnesia can be added to an acid, and the OH and the H cancel each other, and what you get is just more water molecules, and it neutralizes the acid. There's a pH scale, by the way, which measures the total acidity, total amount of base, and this is simply a numerical measure of how many hydrogens or OH there might be. The last kind of chemical reaction I want to talk about are called polymers. Polymers, as you may remember from the last lecture, are composed of long chains of molecules linked together end to end. And the formation of these polymers, the polymerization reactions, are vital to modern industry and to modern society. There are two kinds of polymerization reactions that are very important in modern day life. One of these is called the addition polymerization reaction. In that case, the monomers, the individual small molecules, simply line up end to end. So you have A. When you start with individual small molecules, they become one long molecule. But then we also have condensation polymerization reactions, where the individual molecules not only react with each other, but in the process they release another small molecule. For example, if one of the monomers, one of the small units, has a hydrogen and the other one has an OH group on the end, a water molecule may be released when the two link up. It's also possible, in some cases, that you release CO2, which is a gas. And when that happens, you form a polymer that starts to foam. Indeed, this is polyurethane. You mix two simple fluids together, the two monomers, and they begin to form a condensation polymerization reaction, a reaction that produces CO2 and thus forms the foam. There are commercially available foams of this sort, but in the commercially available ones, the monomers are already mixed. They're at high pressure. When you release the pressure, you can form the same kind of foam for insulation. By the way, the breakdown of these kinds of polymers into smaller molecules is called depolymerization. That's an important part of cooking. Depolymerizing meat or vegetables is what happens when you turn tough meat or tough vegetables into soft, chewable sorts of foods. Museums often have to work very hard against depolymerization because old antique pieces of leather or paper or wood can often be destroyed by depolymerization. Well, in summary, this lecture we've seen that atoms rearrange themselves in two common ways to form materials with new properties. First, we have phase transformations, such as the transformation of graphite into diamond, and they involve the structural reorganization of atoms. And second, we have chemical reactions that involve the combination of several chemical substances into a new one, or the breakdown of a substance into several other chemicals. Well, we'll return to chemical reactions in a few lectures as we investigate the chemistry of life. But next, we examine the properties of materials.